this particular part focuses on two components. One is nonlinear multi-layered composite model for engineered bamboo. So this is the finite element component. And then LCA. So this is actually an engineered bamboo product. And then, of course, also briefly, I'll go into the life cycle analysis of engineered bamboo. And again, both of this work that we present in workshop 1 is background and state-of-the-art review. We will show our results. There are 2 undergraduate students, 1 summer scholarship student working on this, and hopefully they will produce some good results, and we'll present them in our workshop 2. So our objective for this part of the research is to develop nonlinear multi-layered model, because timber is very much anisotropic model. It's a material. It's very not even orthotropic. It's very much anisotropic material. But maybe we can simplify, especially for engineered bamboo like this. Maybe we can simplify into a orthotropic material. So the composite model, and here today I'll be presenting the state of the art. That means what other people have done for engineered timber, and that we can then modify or improve upon for engineered bamboo. And then suitable analytical models for tested beams. So this suitable analytical model, again, would be based on software, finite element software Abacus. Then we will verify multi-layered composite constitutive representation of the engineered bamboo. So they are similar in task. So at the end, what we want to come up with is a way to model the engineered bamboo's behavior, so that we can test, we can try out different combinations and verified by tests. And also we would look at the engineered bamboo sustainability and practicability credentials, select a range of traditional timber-based construction product with uses equivalent to engineered bamboo, which is, we have identified LVL and glue laminated timber to be equivalent, and perform comparative life cycle analysis. So I'll actually show that there have been some very good work already done by international research community that we can build on. So this is again from different papers. We can see they have been able to model the dowel, 24mm dowel's behavior in finite element software, and also the particular connection that we're going to test. They have actually tested in modeled it for pine. So we aim to replicate that or improve that because the Abacus is the same. This is made in the same software that we plan to use. So this is very helpful for us as well. So now, in very short, the right picture show the anatomy of softwood, that's pine, and the anatomy of hardwood, that ash, and you can actually very understandably see that how complex this particular woods are. So they are nowhere near isotropic like the steel or even concrete. And they're much more complex than that. And very simplified model proposed by Shanders in 2012 in his PhD thesis. They actually required to use 9 independent constants to model it, because the simplest way to model would have been transverse isotropy, which would be 5 independent constant. But it doesn't work for natural timber or even natural bamboo, because in transverse isotropy, the shear modulus is not an independent constant, but it is a function of perpendicular Young modulus and Poisson ratio. So that means they are related to the other directions, Young modulus and Poisson ratio. Whereas for wood, they are completely independent. So that means this particular paper actually used, or thesis actually used 9 independent constants. So it became much more complex, and you can see 3 different directions. So longitudinal, radial, and tangential. And then all of them have separate Young's modulus and Poisson ratio and shear modulus. So this is quite complex model. However, and what they did is they actually identified 9 damage parameters, because it's not enough to actually model the elastic part to actually get the nonlinear behavior, the failure. To model the failure or damage, in this kind of timber, you also need to model the damage behavior, which for steel, I'm quite familiar with, or you can say I have my main work on steel fracture simulation. So I've simulated ductile fracture, shear fracture in steel, where we only need 2 damage parameters, ductile and shear. Whereas in engineered bamboo, we actually need 9 damage parameters. And Abacus just by default doesn't provide it. You need to create a user-defined field, user-defined material. So we'll see how far we can go within the short time. We may need to make some simplification for our purpose. And we have also identified, or this thesis suggested what particular method to use for this modeling. And there are different options: classical continuum mechanics, fracture mechanics, hybrid approaches, lattice models. Fracture mechanics is quite, I would say, normally for steel, or if it was isotropic or even orthotropic, I'd probably go with fracture mechanics. However, they suggested, and I agree, that we need to use continuum damage mechanics just because of the simplicity it offers. Otherwise, timber is very much complex material, and to model it using standard fracture mechanics would be little short of a nightmare. So we will be using continuum damage mechanics model for our simulating this. And you can, just to show how complex it is, the Poisson ratio, which is standard, it is quite, we came to believe that it's more of constant, especially for steel. A lot of the materials, it's a constant value, Poisson ratio. But for timber, it is there is a degradation. So with load, the Poisson ratio actually changes. So that's an additional complexity that is that comes with modeling timber. Now, we are not modeling timber essentially, because timber is in 3 directions. They are different. What we are comparing against is laminated vinyl lumber, or LVL, which is cut from, it shows schematic how it is produced. So you will cut this kind of small thin slices from a timber and then glue them together, right? And so in this paper, Just et al. In 2020, recently, they used LS Dyna, and they use this particular material property, laminated composite fabric, and they could, because it's in perpendicular direction to this, it is governed by the adhesive you use. So if we can make the adhesive strong enough, we can assume that the failure will not happen in the adhesive layer. That means we can simplify it a bit. So instead of 9, we end up with 5 failure modes, which are parallel tensile failure, parallel compressive failure, transverse tensile failure. So that means out of plane or out of perpendicular to the grain tensile failure, and perpendicular to the grain compressive failure, and shear failure. So and if we look at the cross sections of the way engineered bamboo are made, engineered bamboo, I believe, could be a little bit more simpler, because we cut, it is usually the small sections are cut and then they're added, compared to LVLs, where you have multiple layers coming from different edge, I think edge circles. So that means there is a weak point in between there, because they are not consistent. Whereas for engineered bamboo, especially with the way they are produced from making it densified, I hope that, at least it makes sense to initially model it as a little bit more simpler, because the main failure would be only, so I intend to model it as a orthotropic material, so only 2 directions, so unlike 3 directions. So it will still be 5 failure modes, but overall the material property simulation should be bit easier compared to standard timber and LVL, but we'll see what we get, what kind of comparison we get. Now, building on that particular paper, this paper in Journal of Building Engineering is a very good paper. They modeled exactly what we intend to model. And again, I'm not going to, for engineered bamboo, but they model for standard timber. So they modeled this screw pull-out withdrawal. So they did this screw withdrawal capacity test, and then also this screw connection test, and they are all standard structural points. And they proposed, in addition to the material property proposed by the PhD student in 2012, they now are proposed to simulate the screw connection using a cohesive interface. Or so again, anyone interested in the audience interested in finite simulation, finite element based simulation, the screw connections, if you remember, the screws screws have threads like this, right? So to model the threads is again a very complex part, especially the contact between the thread and timber makes it very hard to model. It is possible, it just it is not going to convert very easily. Whereas the simplified option is to model this connection, model it smooth, but apply a cohesive, we call it cohesive interface element, or just a friction, we call it the contact property is a cohesive contact property. So that means it increases with load, linearly, it has a linear stiffness initially, but just think about it. If you apply enough force, the thread begins to get loose from the timber, and then the capacity, the connection capacity gradually reduces. So you can model the withdrawal capacity of screw without the really modeling the threads. So that's kind of the advantage of using this method, which we intend to use because we'll be also doing withdrawal capacity tests for engineered bamboo for screws. And this paper actually shows much more in-depth details, what kind of meshing we're going to require. You can see the results are quite good, and especially the stress distribution, damage, all this are quite well. So we are happy to have found this paper. Then that's for a guide that we can use for our engineered bamboo test simulation as well. And to simulate this, we are going to need this kind of information. Actually, this we can simulate, but we are going for the material property. We're going to need the transverse stiffness, perpendicular to grain stiffness, parallel to grain stiffness, shear modulus. So this is some information I expect the other university partners will also be able to get during their test. So I hope that we can share this information, or we can, once we are able to develop this particular model, we expect that we will be able to test, simulate some of your models as well. So this is another paper where connection performance of timber concrete composite slab inclined self-tapping screw with self-tapping screw. So this is an inclined screw self-tapping, and this is timber, and that's concrete. There is a steel plate to apply the load. So it's a bit more complex to model, and we need a bit more elastic modulus information. But fortunately, again, more you can say I'm bit encouraged to see that they are able to simulate it within relatively the transverse orthotropy, the orthotropic simulation that I just discussed, and a constant Poisson ratio. So if this simplified method works for them, for engineered bamboo, it should work. So that means at least initially we should be able to get some results, and anyone who are interested in modeling engineered bamboo behavior, you can refer to this paper as well. It's very recent and just published this year. You may be able to get, and this is the cohesive contact definition that I was referring to. So to model screw connection without the thread itself, the contact behavior needs to be modeled like this. So initially, up to this displacement, deformation, the traction increases with displacement. The more you pull, the more load you need. But after a while, after a certain range, when the thread has actually made some significant deformation, the timber is no longer able to hold it. So then gradually with deformation, the traction reduces. So this is something we can simply model without really having to model the thread on other connections. So I will not go into this particular detail. This, again, another paper which modeled bolted connection, but we are not focusing on that. And now I'll just very quickly, for the sake of time, go to the LCA, the life cycle analysis component of it. And Again, I'll refer to the Moso Bamboo work. They have done very good work in terms of getting all this certification, and the data are publicly available. So I'll recommend please have a look and see what kind of, whether you can do similar for other places. This is done for Netherlands, of course. So for our research, for our team, we need to do it for Australia, US, UK, and Brazil. We intend to, for my student, who is working on life cycle assessment, who will be looking for Australian perspective. And what we found to be very interesting is that Moso Bamboo, the report concluded that manufacturing the Moso Bamboo products in China, shipping to Europe, and end-of-life disposal of the material by incineration for electricity generation in the Netherlands had a net negative carbon footprint. So that's very encouraging. If that works for Netherlands, because they are shipping it from China, that we expect that we will probably also work for Australia, because we'll also ship from China or Brazil for different bamboo. So we do have the base that we can compare against, or we know exactly what type of information we require for comparison. And this publication, they provide a lot of information here, especially environmental product declaration. They provide a lot of like acidification potential, global warming potential, biogenic. All this information are required to be able to properly compare all the environmental impact. And this is something we are looking for. I think most of the case for Moso Bamboo should be the same. We'll only need to look for the Australian component. However, for a new material like Bambuild, you would eventually need to get this information as well. Wood and Australia's carbon balance is quite fraught, and the way our standards are set up does not allow, at least this is quite old, so I'm not sure what happened now, but I believe it's still the case. It does not allow us to consider the carbon sequestration that happens in these timber houses. So that means the carbon storage that happens in the forest or the timber houses. So that means building with timber is disadvantaged because the way the calculation is done. However, globally, there is a push to consider the carbon storage in this kind of life cycle analysis, and we will intend to do that in our case as well. So here, this shows the carbon dioxide equivalent for different materials. So concrete slab is very high, steel subframe, you can see timber is almost 1/6 or less than 1/6 of that. And for different parts and for all parts, they compare the timber products compare very favorably. And I'll show in a moment that engineered bamboo is even better than timber. So we have a good case for life cycle analysis wise for engineered bamboo. So I'm again not going to all this. So just to mention that life cycle assessment generally treat carbon dioxide emission as a burden, but the storage of the carbon in trees and its in long-term storage in wood products are not acknowledged, which makes it, especially in Australia, so it makes it disadvantage the timber product. And here I also would like to point out one thing is that because engineered bamboo or because bamboo grows so quickly, right? So what happens is you can store more and more carbon, much more amount of carbon in the same area, because within 5 years you're planting new trees, and then they are going to maturity in 5 years again. So in a hardwood species wise, you will store it for 50 years too, but you can store you can actually get 5 times more or 10 times more houses and get them stored in house, right? From the same amount of land compared to hardwood, because hardwood would take 50 years to store that amount, store that equivalent amount of carbon dioxide. So we need to highlight that component. And this particular paper by Lee et al. In 2016, they did a good comparison of glue laminated bamboo, which is essentially the engineered bamboo that we're talking about. And they compared quite in-depth comparison, performed quite in-depth comparison of different steps, different parts. And what they found was quite interesting is that and these are acidification, so I just put them side by side so they're easy to see. AD is abiotic depletion, acidification potential, eutrophication potential, all these potentials, global warming potential, all. And the impact of different components is highlighted here. You can see the main culprit is the urea, the fertilizer, the nitrogen fertilizer that's required to make bamboo. So if we can minimize this, there is this is usually bamboo requires less amount of fertilizer anyway, but again, if we can even minimize that anyway, that would be even beneficial for life cycle equivalency. And the different processes, carbonization, drying, planing, gluing, hot, the different stages of engineered bamboo production, they are also relative contribution is shown here for different components there. So I would again suggest that you look into this particular paper by Lee et al. The reference list is at the end, and it is exactly what we plan to do, but for Taiwan's perspective, we would do it for Australian perspective. So there will be some changes, but mainly a lot of the things will be common. So for other bamboo, and I think we discussed yesterday, for another the bamboo dust post planing. So that means when you make it plane, is normally recycled and sold to solid fuel processing plant. Thus, the environmental load caused by bamboo dust processing and burning was not discussed in the paper. So this paper did not account for the solid fuel and the carbon dioxide that was generated by burning it. So that's one disclaimer here, but that's something we'll probably account for. And you can see there are other paper by Cheng et al. In 2018 on the environmental benefit of utilizing bamboo material based on life cycle assessment. And they have provided quite in-depth power requirement for different parts. So I found our students are finding it to be very useful. So, for their life cycle assessment calculation. And then all the engineered from Moso bamboos, particularly focuses on Moso bamboo. So all the different stages have been accounted for, and quite detailed information is there with regards to what at different stages, what kind of impact it has. So bamboo harvest or transport, so different stages are there. And they have compared two particular scenarios. So this is when you bleach treat it. And another comparison is actually the same comparison, but this is for heat treated. So I'll show in a moment that they found the impact of ply bamboo or this particular bamboo is more for bleached, so less for bleached than heat treatment. So if the treatment part is made by bleach or similar I think chemicals, which for bamboo build is I heard it's more environment friendly. It would be probably even better. So this paper compares those behavior, and actually can see under climate change that's a negative effect. So it's not only zero, it's negative. That means it's helping with the climate change scenario, and all the values are there. So these are very useful paper and useful information that we'll be using for this project as well. It compares against concrete, concrete, steel, and others. So although for some part of concrete, it seems to show very low carbon dioxide emission, which I do not agree. I will need to check why that happens. But you can actually say carbon storage wise, bleached and heat treated bamboo and ply bamboo, they are negative. So compared to others, the others cannot. Naturally, they cannot store any carbon. So these can, and because they can, overall carbon dioxide emission is negative. So you can see the engineered bamboo will be able to be net negative in terms of equivalent carbon dioxide, so which is very promising. And it also shows the different effects onto carcinogens, non-carcinogens, respiratory inorganics, global warming, all these factors, and most of the cases, plywood would do very, very well compared to other type of products. And these are only the main components: the resource, climate change, ecosystem, and quality. You can see compared to aluminum, PVC, reinforced steel. Again, I do not know what happened with concrete, and they seem to be favoring concrete quite a lot. then needs to, I do not agree with that particular part, but you can see for ply bamboo under bleached or heat treatment, and there is a negative impact on climate change. So that, sorry, I mean, positive impact on climate change or negative climate change impact. So that means it is, we can do it enough, we can reverse to a certain extent, or at least negate the impact of other materials, other components. So that's very good. So that this particular PhD actually looked directly compared CLT against cross-laminated timber against engineered bamboo. They modeled in Revit, and they looked at structural components, exactly what we intend to do. Although we wanted to do for residential house, they did it for full-scale house, but they also provide very good information. And I'll just go to the end. You can see here the carbon dioxide equivalent for engineered bamboo, which is the purple, is lower, and also only on non-renewable energy, because the way the amount of energy you need to produce it, only these two get strong smoke formation potential, and non-renewable energy, that's only bamboo is higher. In all other cases, bamboo is significantly, so it is comparing apple to apple, right? So it is comparing the engineered bamboo against CLT. So both are engineered timber and engineered bamboo. And even in that comparison, for structural application, engineered bamboo was found to be better. So that's very, very encouraging for us. And our students will try to replicate it for Australian scenario. So that's all. And we will be using the same software that most of these papers have used. So the Gabi, so that's all from me. Thanks for listening. And if you have any questions, I'll try to answer very quickly.